All right, we're solving some complex numbers now. So you can see there's an addition of an x and a y. We were trying to solve for both x and y in this example. First step would be similar to what you would have done before in algebra. Multiply the brackets, which we're good at from yesterday, of course. X times the 1 gives an x. X times the minus I gives minus xi. These two together give plus 2i, and the final two multiplied together give minus. Oh, it could very well be. This times this. Yeah, and then we're here. Now this one, yes, we're going to change in a second. You've noticed already. I squared is minus 1. So you can do this, and then you can do this.
Is that just 1 minus I?
1 minus, here, yeah, that's 1 minus I, yeah. Okay. All right, we're kind of at a roadblock a little bit here. How do I finish this? How would I, like this, is I an unknown is a variable?
Not technically.
Not technically, it's just not. Yeah, it's, we know what it is. It's root minus 1.
And would you get all the i's on one side and then just get rid of the i's? I feel like that's not very...
It's a decent strategy. So let's try that. Let's put plus 2, these two, and then minus the 5 here. And then
I as a common?
You
take the I as a common?
yi plus xi. We're just getting to this stage plus 2i. So we have i's on this side and that on that side. What would be a next step, Abby? I wouldn't probably take this down because it's not the right way to do it.
No, because you can't get rid of the I, because if you divide it by I, then you will obviously
get rid of it.
Yes, it should be minus 2i, you're right. I'm going to rub it out anyway because it wouldn't be the way I do it. But you're taking it down, but yeah. This probably, yeah, you're letting the real equal the imaginary, but does the real equal the imaginary? No, in this case, this should total to this if we knew what x and y are, but both variables are over here with the imaginary, and there's no only one variable over here with the x. We're trying to get x and y equals.
So there would be some sort of simultaneous equation.
I'm going to get rid of that.
Or then you just use substitution, y equals this, and
Well, yeah, that would be more similar. We need probably a second equation to do that. Let's just look at an example. If I know 5 plus 4i is the same as x plus 4i, what's x?
X is 5.
X is 5. So the real must equal the real on the other side. The 4i doesn't really affect. Okay? So if I change this to x plus yi, what is x?
X is...
Still 5. Because the real must equal the real and the imaginary must equal the imaginary. So 4 must then equal y. We follow that? So what we've done, we've set up that the real equals the real on one side and the imaginary equals the imaginary. We kind of form two equations out of that. So what we have here then is real and imaginary on this side and real and imaginary on this side. But I know that the real on this side must equal the real on that side. Let's just take the real. X plus 2 equals 5. We see that? Any real bits must equal each other. And on the other side, we take the imaginary part of the number.
2i minus xi equals 5 plus yi.
Yes?
And we have... Or just yi.
If they have all i's in them, do we need them?
No.
We don't need to write the i's every time. If everything, so if you have a statement like this, x over 2 is equal to 5 over 2, you probably don't need to write over 2 anymore. X just equals 5. So the same thing here. If the I is in common, you can factor it out if you want. But if the I is in common, we already called this the imaginary side. I have negative x, I have plus 2 of them, and I have equal to y of them. And I don't need to write I anymore. I will get a solution then for x and y. X here clearly is 3. And y here is what? Yes, once we have this x value, I can put it in. I think it might be negative 1, is it? Because I have negative x, and positive x is 3. So negative 1 is equal to y. So what was the thing? If you have an equation like this, the real equals the real, and the imaginary equals imaginary. Oh, spell it right.
So just splitting it up in things without an I.
Exactly. Yes, you split it up. Because of this.
Substitute the x in.
All right. All right, so we'll do some of these in a few minutes. Maybe I get you guys to do, no, I'll do it in a few minutes. Let's talk about conjugates from yesterday. If 5 minus 4i is a complex number, z, what is z with a little star on it, a conjugate? What? 5 plus 4i. Okay, that's a conjugate if you remember. It's the thing that will make the denominator real if we need to do a division. Okay. It's like rationalize the denominator. Yeah. What was the word we used yesterday? Realizing the denominator now, yeah. Okay. So we're going to look at two. We won't look at this one because it takes a while to multiply, but we will look at two complex numbers. Which one will I pick? Let's call it Z1 is 1 minus I, and Z2 is 2 plus I. We're going to look at a couple of calculations with these. We're going to do the conjugate of a conjugate.
It's just the original form.
Is it?
No.
What's the conjugate of a conjugate?
Something.
So that'd be
Z2?
1 plus I, wouldn't it? The conjugate of that. So I've done the inside bit. The conjugate of Z1 is 1 plus I. What's the conjugate of that?
1 minus I.
1 minus I. So you're right, Abby. The conjugate of a conjugate, if you double conjugate, it kind of cancels each other out. The sign just switches back to negative. So I can say a conclusion if I conjugate a conjugate, which is using that word way too often, I get the original. That's one conclusion I can make. Now, we prove that very easily. Okay. Let's look at a second one. Z1 plus Z2. If I do that and then get, so if I add them and then get the conjugate. So 1 minus I plus 2 plus I, so I've added Z1 to Z2 here. What do I get? I'm going to get the conjugate of that in a second. It's 3, yeah. That in itself is not that special. Yeah.
Whoa! What's up, sir?
Back in the day.
Do you have any log in detail with you for the website?
No, I've seen you have it. Yeah, thanks.
No, because the one of the two I'm changed.
Okay. What we're going to look at is if I conjugate before I add, do I get the same answer? So if I conjugate and then add, what answer do I get? Is it going to be 3 as well? Well, let's see. So the Z1 conjugate is 1 plus I, and this conjugate is 2 minus I. Same answer. You do. Yeah, you do get the same answer. Because the I is still canceling, you get 3. So it doesn't matter if you conjugate after or before in this system. So that's another conclusion we can say. Let's write that Z. Two complex numbers, if you add them first and get the conjugate, is the same as if you added the two conjugates, which is kind of a, they're all mouthfuls, yeah?
What about in a situation where you don't cancel out the
If the i's don't cancel out? I suppose, yes. What you could do in a lot of these cases is instead of picking one example, which is what we're doing there, we pick every example. We could call Z1 A plus BI and Z2 X plus YI. And that just accounts for any variable. So maybe we'll do it with this one, just to prove it. So I know I've used z again, but let's just look. If I add them first, I would get a plus bi plus x plus yi, which gives what? A plus x as the real part, plus b plus y. We'll put it as a, okay? So I'm just doing it in general. And then I'll do this one with the same system and see do we get the same answer. Oh, I haven't got the conjugate yet, sorry. The conjugate then is what? Yeah, a plus x minus b plus, whatever answer b plus y was, you'd now have a negative. You following me? I'm just doing it. Sometimes they ask you to prove these, and if you need to prove them, you can't just use one example. You've got to use an example where it could be any variable, because it's got to work every time, not just once. You don't have to, but if you want. Okay, then do the conjugate and then add. So now we'll do this one, conjugate first. So a minus bi plus x minus yi. We happy with that? So it's still a plus x. And now I have this, minus bi minus yi. Is that the same? Yeah, if we factor out a minus 1, and this is how you'd prove it. That's proved now. This is just an example, proved. So it does work every time. Okay, there's a number of these, and it will take us a while to do them all, but they're kind of repetitive in the way, so I'm just going to write the rest of the conclusions. This is important. I was going to do this at the end, but might as well do it now. This is how we prove. So if a question asks you to prove, you can't just use one example. You create two with variables that could be anything.